Can light physically move a mirror? I mean, it sounds like a simple question, right? We usually just think of light as this thing that illuminates our world. But here's the crazy part. Light actually has momentum. It pushes. And that physical push, what we call radiation pressure, is quite literally the key to unlocking everything from the absolute weirdness of the quantum realm to the deepest, darkest mysteries of our cosmos.
Welcome back to another Explainer. I am absolutely thrilled to guide you through this one today because we are exploring the incredible world of cavity optomechanics. Now I know, it sounds like a bit of a mouthful, but stick with me. By the end of this, you're going to see how manipulating something as simple as light and matter is totally revolutionizing our understanding of fundamental physics. We're talking about controlling microscopic interactions to build next-gen quantum tech and even, get this, hunting for dark matter.
Okay, let's just dive right into the roadmap. 1. Light's physical push. 2. The quantum limit. 3. The quantum bus. And 4. Hunting the unknown. This whole journey is going to take us all the way from a microscopic photon hit right up to cosmic quantum gravity. All right, kicking things off with Section 1, light's physical push, the power of radiation pressure. To really grasp what's happening at the bleeding edge here, we need to quickly ground ourselves in exactly what this field actually does. So cavity optomechanics is all about having light interact with a mechanical system in a very controlled way, via radiation pressure. And that's usually mediated by a cavity. Think optical or microwave cavities. The absolute game changer here is that word controlled. By using this specific interaction, scientists can manipulate both the state of the light and the state of the mechanical system. And since mechanical systems come in, all shapes and sizes, this gives us a completely brand new way to manipulate light and matter across the nano, micro, and even macro scales.
Now, the roots of this actually go back way further than you might think. Picture this. It's 1909. The light quantum hypothesis is still being hotly debated, and Albert Einstein proposes this brilliant Gedanken experiment, a thought experiment. He imagined a perfectly reflecting, moving mirror inside a black body cavity filled with gas. And he asked, how exactly does energy transfer from the radiation field to that mirror to achieve thermal equilibrium between the gas, the radiation, and the mechanics? Fast forward to the 1960s, and we've got Vladimir Brzezinski pitching early ideas for actually utilizing these radiation pressure effects. But honestly, it wasn't until the 2000s, with this massive explosion in nanomechanics and integrated optics, that these effects became widely accessible in the lab.
Now, what's really interesting about this slide, and monumental about Einstein's early question, is what it actually proved. When you sit down and analyze the radiation pressure-induced mechanical position fluctuations of that mirror, you find two totally distinct contributions. First off, you have the wave nature of light. That causes fluctuating radiation pressure just due to simple interference. Totally standard classical physics, right? But then, there's this second contribution that can only be explained by the particle nature of light. It beautifully illustrates that you absolutely need both the wave and the particle characters of radiation to get a complete, accurate description of an optomechanical system.
Moving right along to Section 2, the quantum limit, when measuring destroys the measurement.
Of course, as you know in physics, with great precision comes great complication. Not all of these radiation pressure effects were immediately useful. By the 1960s, researchers realized quantum mechanics had thrown in a major nuisance. There's this ultimate limit on the intensity fluctuations in a laser beam, which we call shot noise. And when scientists started building massive, large-scale interferometers to detect gravitational waves, projects like LIGO, this suddenly became a really pressing issue. So Carl Kayes published this seminal paper asking a super crucial question. How do these quantum mechanical radiation pressure fluctuations actually disturb our measurement of the free masses inside these massive detectors?
So you might be sitting there thinking, well, just turn up the laser power to get a clearer signal, right? But it's a total trap. As you increase laser power, your measurement noise, that relative intensity fluctuation, does indeed go down. Awesome. But wait for it, the back action noise, which are the physical disturbances imparted by the radiation pressure on the mechanical system itself, that actually goes up. So the harder you push the laser to get a clear read, the more it literally shoves the mirror around, completely ruining your reading. Talk about frustrating.
This brutal trade-off creates what we call the standard quantum limit, or SQL for short. Essentially, it's the minimal phase noise that can be reached at a certain laser power when the integration time is kept constant. For a really long time, this was just a hard ceiling. Nobody could get past it.
But researchers at LIGO didn't just give up. Through sheer ingenuity, they used a combination of squeezed input light and ponderomotive squeezing through optomechanical interactions inside their long baseline cavities, and no way, they actually achieved measurement capabilities below the standard quantum limit. Absolutely incredible. And this slide brilliantly illustrates how they approach this in other quantum regimes. Look, if you just have a standard micromechanical membrane sitting alone in a cavity, you're going to hit the high fluctuations of the standard quantum limit every time. But if you add another degree of freedom, specifically something like a negative mass oscillator, say an atomic ensemble with an inverted spin in a magnetic field, you completely change the game. You essentially create a quantum mechanics-free subsystem. The result? A back-action reduced system where position measurement can, in principle, be done with arbitrary accuracy. You literally just circumvent the noise entirely.
All right, let's shift gears to Section 3, the quantum bus, translating the quantum world.
See, optomechanics isn't just about avoiding noise. It is about actively connecting disparate systems. I absolutely love this quote from the source material. It says, "The mechanical system can serve as a bus between light and other degrees of freedom that would otherwise not directly couple to photons." Just think about that for a second. A mechanical solid-state system can be functionalized. You put a mirror on it, bam, it couples to photons. You put a conductor on it, it couples to charge. The physical mechanical movement basically becomes this universal translator, a bus transferring quantum information between totally different forms of energy that would normally just ignore each other.
And this exact concept solves one of the absolute biggest outstanding challenges in quantum computing today. How on earth do we interconnect microwave-based quantum processors over long distances? Well, here is the step-by-step solution Optomechanics gives us. Step 1. The microwave signal from the quantum computer gets converted into mechanical energy, like an actual physical vibration. And this is often done using a piezoelectric material. Step 2. That physical mechanical signal is then converted into optical information using an optomechanical interaction. And finally, Step 3. Now that you have an optical photon, you can easily just send it over massive distances through standard optical fibers. The mechanical system acted as the absolute perfect bridge.
The sheer versatility here is honestly staggering. Let's rapid fire through some of these amazing mesoscale applications. For medical tech, we can up-convert MRI signals to the optical domain. That means we can move the sensitive receiver electronics far, far away from those noisy high magnetic field coils. Then there's phonon routing. We can use phonon waveguides to route physical vibrations, building interacting microcircuits of photons and phonons completely without piezo materials. We can even achieve on-chip quantum memory. By strongly modifying the dispersion relation, we change the group velocity of light, which lets us literally store Fourier components of optical pulses right there on a chip. And check this out, if we use complex topological geometries like a snowflake crystal, we create pseudomagnetic fields that allow for robust, topologically protected sound wave transport right around obstacles. It's basically directing traffic for sound and light at the quantum level. Mind-blowing, right?
Okay, bringing it home with Section 4, hunting the unknown, using mirrors to probe the fabric of reality.
Now, you might want to take a breath here, because we are transitioning from some incredibly cool technological applications to literally probing the fundamental fabric of reality itself. These optomechanical sensors have become so breathtakingly precise, they're opening up an entirely unexplored parameter regime for fundamental physics. Just look at what they're hunting: dark matter. Most dark matter candidates would subtly affect the motion of massive solid-state objects, which makes these sensors the ultimate trap. Dark energy. Theories actually suggest scalar fields responsible for dark energy might cause these tiny short-range forces. Scientists are testing this right now by bringing levitated particles incredibly close to a gold plate, just to measure those microscopic interactions. And they're even probing Newtonian gravity, looking for deviations from the standard inverse square law at previously unachievable tiny micron scales. And guys, it gets even deeper than that. Optomechanical sensors can actually provide bounds for theories of quantum gravity, and they can do it right inside a laboratory experiment. Theories that are attempting to unify gravity with the standard model suggest that at low energies, there might be modified dynamics. We're talking things like modified commutators or non-local effective field theories that actually generate observable consequences, things like geometric phases, mechanical anharmonicities, or time-dependent mechanical squeezing. With sufficiently good optomechanical quantum state control, we can finally measure these effects in a lab setting.
But really the ultimate prize here, the true final frontier of this entire field, is directly probing the quantum nature of gravity. As the source material notes so perfectly, up to now, we only have experiments that show how a quantum superposition behaves in the presence of gravity.
To test the reverse of that, we would have to entangle massive, high-density objects using their gravitational interaction just to see if a space-time metric can actually exist in a superposition. Mechanical systems in the quantum regime are uniquely suited for this, simply because they are the only systems to date that combine large mass, high density, and large coherence.
Which leaves us with this final, incredibly thrilling question. How does gravity behave in the presence of a quantum superposition? Can reality itself exist in two states at once? Cavity optomechanics, starting all the way back from a simple mirror pushed by a beam of light, is finally giving us the tools to answer that. As our source perfectly puts it, if exploring the gravity-quantum interface isn't fun, what is? Thank you so much for joining me on this explainer. Keep questioning, keep learning, and I'll catch you next time.